All right, so first section that we're going to talk about is section R1 in the textbook. The R is kind of a review type section. So any of the sections that start with R are going to be reviewing material type things. So we're going to start by talking about sets, and this may be the least mathematical of the sections that we talk about today, or pretty much the whole course. But it's kind of more of a learning about the number systems and the different kinds and all the things that we can deal with out of that. So when we're dealing with sets, a set, the definition is just a collection of objects. And in our case, it's normally going to be numbers that we're going to have in our collection. And each object in that collection is called an element. That's a piece inside of a set. And the notation for element is the Greek letter epsilon, but the lowercase version of that. So the best way to draw that is just make a lowercase c and then put a little line in the middle of it so it looks almost like an E. So that's the Greek letter epsilon. And anytime you see that you read that as is an element of is what that stands for. So when you see that notation on the quiz or on the lab, that's what that means. It means whatever's listed first is an element of a particular set. Sets are noted in braces, and they call them set braces, and it's these curly brace. It's not a square bracket, it's a curly kind of brace out of that. So it's okay, got a point in the middle. And curly braces is set braces. Brackets mean another thing later on, so don't confuse those. And parentheses are not the same thing as set braces. So an example of that would be, we could have a set. We might call that set S, and it's equal to this set of objects: 1, 2, 5, and 7. Just making up that really those numbers don't mean anything. They're just pieces of that set. In that, using that example, we can use that element notation. We could say that 2 is an element of S, because 2 is an object that is inside of that set S. So 2 is an element of S. So that's how you would read that. 2 is an element of S. If you see this notation, maybe like 3 and then the epsilon with a slash through it, that means that 3 is not an element of S. That's all that means. So you would read that 3 is not an element of S. So epsilon with a slash through it just means not an element of. Epsilon, lowercase epsilon there is just element of. So you'll see that notation some as we go along here. All right. When we're dealing with sets, there are different kinds of sets. There's a thing called a finite set. F-I-N-I-T-E, finite set. A finite set is has a limited number of elements. I always relate that a finite set, you can count how many pieces are in it. Okay. Examples of finite sets are like the set S that we've got written here. It has 4 pieces, 4 elements in it. It's a finite set because it ends. An infinite set it's unending. or unlimited. In the number of elements. Okay, an infinite set would, if you just said all the natural numbers, they're infinite because you could always keep counting higher. The natural numbers, for example, when we're talking about the natural numbers, let's list that because we're going to need to know some of these different kinds of numbers. The natural numbers, the notation for natural numbers is a capital N, but then they put 2 bars in the middle. So they double that bar in the middle. That's the short hand for natural numbers. The natural numbers are the natural counting numbers. So when you teach your kids to count, you start with, well, 1, 2, 3, like that. And so the natural numbers are those numbers. But they keep going, right? Forever. So the natural numbers would be an example of an infinite set because it never ends. Because you can always count one higher. Right? Another example of an infinite set would be just a random set. We'll call this set A. Maybe it's start with the number 1. The next element is 1/2. Next element's 1/4, 1/8, and then it has this dot, 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 and in there. So when you see that dot, dot, dot at the beginning or the end of a list that's a set, that's clues to tell you that's an infinite set. It's an infinite set because if we continue this pattern with these fractions in this problem, you'd have after 1/8 it's going to be 1/16, and after 1/16 it's going to be 1/32. And you just keep that pattern going. And it's an infinite set because that pattern can continue forever. So this would be an infinite set. So infinite sets keep going forever. So that's what we want to get out of there. A finite set, an example of a finite set might be something like this. 7, 8, 9, dot, dot, dot in the middle, and then maybe it goes up to 15. Even though it has the dot, dot, dot in it, it's not at the end. We're seeing a set listed starting at number 7 and going up by ones, and it's going all the way to 15. They don't list everything in there. We could infer what is in there. We could list it out if we wanted to. But we know that this is a finite set because it ends. So big thing here is just being able to distinguish between an infinite set and a finite set. Finite has an ending spot. Infinite does not. Okay. Another way that they might write a set would be like this. They might use curly braces, and then they may put a variable in there like x, and then they'll put this straight up and down bar, and then they might have an inequality, and we'll do that. And the way that that's read is x such that x is between 9 and 13. That's how that set is read. X, and then the straight up and down bar is the such that part. And then this inequality says, okay, x is between 9 and 13. Would this be an infinite set or a finite set? Does it have an ending spot? Yeah, it stops at 13, doesn't it? So this is a finite set because it has an ending spot. All right. So let's look at some examples of things that we do with sets that are listed. And one of those things that we do is that the instructions might say list the elements in each set. And the way that they're going to present the set to us is using that notation x such that x is a natural number less than 7. Okay, so they write out this statement and say, okay, list the elements that fit that. Okay, so if we're going to list the elements that fit that, natural numbers are the counting numbers, 1, 2, 3, 4, 5, and so on. But this one says only the ones that are less than 7. So that would be the numbers 1, 2, 3, 4, 5, and 6. We don't include 7 because it said less than 7. So that's why we stop at 6. And this would be the set that lists all the elements of that particular set. Okay. So very basic idea of what one of the things that we do with sets in this first section. Let's try another one. Let's say we had a set that's described this way. X such that X is a natural number greater than 7 and less than 14. Natural number, greater than 7, less than 14. So what are the numbers that are in that set?
8, 9, 10, 11, 12, 13.
Do we include 14?
No, sir.
Good. Very good. Easy stuff there with the sets out of that. All right. So a couple examples of one of the basic things that we do with sets out of this particular section. All right. So let's talk a little bit more about sets in general. When you're talking about sets, there's a thing called the universal set. Universal set. The universal set is basically everything in a discussion. And a discussion means a problem. Okay, so what you've got to look for is if they don't tell you what the universal set is, but maybe they say that in the set of natural numbers, well, then that tells you, hey, the universal set is the natural numbers. So it's the big umbrella over everything part of the conversation or the problem that you're dealing with. So the universal set is going to be the big picture. Okay, that's the way I always think about the universal set. There's another thing called a null set, N-U-L-L set. It is also sometimes called the empty set. So those are synonyms. The empty set would imply that it's empty. It has nothing in it, right? So it's an empty set, no elements. The notation for the null set or the empty set is a set of empty braces. The curly braces just empty. Or sometimes you will see it listed as a circle with a slash through it. Either of those means the null set or empty set. Okay, that's the notation for that. So if you see the null set or empty set, the notation that goes with it is going to be the empty braces or a circle with a slash through it. Either of those would work for that. All right. Another thing, kind of definition thing that we're dealing with here is a subset. A subset is taking part of a larger set, right? Subset, sub-organization, kind of, it's a smaller part of that. So it's a smaller group of elements from a larger set. Okay? So that larger set may be the universal set. It may be just a larger set that they're defining for you. They're just telling you, hey, I've got the numbers 1 through 20 here. That's the bigger set. And the subset might be the even ones. That might be a subset of that. So that's a good example of subsets. So let's take an example here. And let's say we have set A. And we're just going to list the numbers 1 through 8 for set A. 1, 2, 3, 4, 5, 6, 7, 8. And set B is another set that has the numbers 2, 5, and 7 in there. Curly brace didn't look real good there. Let's fix that. Okay. And the question that we want to answer is B a subset of A? And to be a subset, everybody inside of the subset has to be in the larger set. So let's look at the elements in set B, 2, 5, and 7. Are 2, 5, and 7 in set A? Yes. So B is a subset of A. So this will be the answer to that would be yes. Now, let's talk about notation about how to write that. And the notation for subset, if I say B is a subset of A, that's the notation for that. B is a subset of A. It's kind of like, it's not really a C. It's more of a kind of a sideways U shape with a line under it. And that says B is a subset of A. That's how you read that. So the notation for subset is kind of this sideways U shape with a line under it. That means subset. Let's look at another one. Let's use the same set A. So I'm just going to copy that one. If you want to just refer and say set A from example A, you can. I don't know why I made that example A. It should actually be example C because we already did A and B. Don't need to do them again. I'm going to change those letters just because my OCD can't let it stay the same. So same set 1 through 8 for set A, and let's get a set C that has maybe 6, 10, and 20 in it. And the question is the same question. Is C a subset of A? And I'm using the notation this time to ask that question instead of writing it out. So, is C a subset of A? No, because we've got 6. It is part of it, but 6 is only part of the set C. It's also got 10 and 20. Both of those are not in A, so there's no way that the set C is part of set A. So this is definitely not. The notation that you could use to say that would be C is not a subset. So the way to say not a subset is just subset symbol with a slash through it. Not a subset of A. That's what that says there. So subsets, everything in the smaller set has to be in the larger set. If they're not, then it's not. If everything in the smaller set is not in the larger set, then it's not in there. Okay, that's not a subset. Okay. All right. Another thing that we deal with in sets. You may or may not remember this from long ago. A lot of my high school kids don't remember these because they just don't do them very much anymore. Y'all remember doing Venn diagrams? You may not remember the name, but I bet you remember the shape. Remember doing those things? You had circles and they had the football shape in the middle, and you had a set A and a set B. And the way that Venn diagrams work, and I'm just going to define a couple of sets here. Set A is going to be the numbers 3, 5, 7, 9, 11, and 13. Set B is going to be the numbers 6, 8, 10, 11, 13, and 14. Okay. Now, if I go to put those sets in the Venn diagram, what should go in this football shape that's in the center? That is correct. The numbers that are in both A and B. So for this one, 11 and 13 are in both of those. So 11 and 13 goes in the football shape in the middle, or in the overlap. The correct mathematical term for that is intersection of those two. And then over here in this part of the bubble, are going to be the rest of the elements in A. So the rest of the elements in A are 3, 5, 7, 9, and that's it. 11 and 13 are also covered there. And then in this part of the bubble over here are going to be the other elements that are in B. So that'd be 6, 8, 10, and 14. We have those numbers listed there. Okay. Again, this part in the middle is called the intersection of set A and B. The notation for intersection, the mathematical notation for that is an upside down U, like that. Intersection is the upside down U. The intersection is the overlap. The intersection, the elements in the intersection we know are 11 and 13. That's the only numbers that are in both of those sets. So that's how we list the intersection of two sets there. And then the next thing, we're going to use the same example. We're going to talk about the union. The union is a complete list of all elements in both sets. My wife and I got married, called the union of marriage. I got everything she had came with her. In-laws and everything, got it all. And she got all mine too. So I don't know who got the best end of the deal. I'd say I probably did. So the union is just that it's everybody. Everybody's in the pool. Okay. So the notation for union, I think, is the easiest one to remember. It's in, intersection is that upside down U. Union is A, and then it's a U. It really is a U. Union B, and you just list out all those elements. And the elements we had started at 3, 5, 6, 7, 8, 9, 10, 11, 13, and 14. So it's everybody that's in there. And you don't list an element twice because it was in the intersection there. You only list it once because it's in there. All right. So union is everybody. Intersection is the overlap. And so really Pretty easy concept. Venn diagrams can really make that really easy to see or read from. I think if they give you a Venn diagram, it's much easier to see the intersection than it is if they give you two different sets completely. Sometimes it might be easier for you to actually, if they list out the sets, make a Venn diagram so that you can see that intersection more clearly and easily out of that. So Venn diagrams, useful thing out of that. Let's look at some sets that are just listed and as an example here, and see if we can get the notation and all that stuff under our belt a little bit better. So let's say set W, just to change up letters, 9, 15, 25, 36, X, 15, 20, 25, 30, 35. Okay. First question is the intersection of W and X. 25 is in there. Is there anything else? 15 is in there as well. So we're going 15 and 25. Oops. Curly braces are not working today. There we go. And then obviously the second question is going to be the union of those two. So go through there, and we know we're not going to have to list 15 and 25 twice, just once. So the union is just put everybody in the pool. So 9, 15, 20, 25, 30, 35, and 36. It's not a requirement that they be in numerical order, but that's how you're going to see them most often. If you didn't put them in numerical order, no big deal. But most of the time, you're going to see them that way. You'll see them that way on the Canvas quizzes. They'll be in numerical order. On the labs, like I said, it's not a requirement that they be in order. I kind of just do that out of habit because I know that's how they're going to end up being listed as answers. But I wouldn't take off points if you didn't list them in numerical order out of that. Just understand that that's how they normally are done. Let's take another example. Really easy one here. We'll do a small set just so we don't have to write so much, just to get this concept down. 1, 3, and 5 for set G. Set H, let's do 2, 4, and 6. And let's say they ask us to list the intersection of those two. There's not one. So what set shows us nothing? It's that empty. Yeah, the empty set, that null set. Remember the empty braces? That would be one way. Or if you wrote it this way, either of those is absolutely fine for that. So the empty set, or that symbol there, the null set, empty set idea there. Okay. So null set, empty set, if there are no common elements in an intersection. If I ask you to do a union, will the answer ever be the empty set? No. Unions always have parts. Intersections could possibly not have parts there. Okay. All right. This first section, last thing that we're going to talk about in this particular section is a thing called the complement of a set. So complement, COMPLEMENT, not complement with an I, complement with an E of a set. A complement of a set, the definition of that is the elements that do not belong to a set normally from a larger or universal set. So I think the best way to kind of show complement of a set is to actually just do an example. So let's take set A, and let's just do the numbers 1 through 7. 1, 2, 3, 4, 5, 6, 7. And let's call set B. Let's do the 1, 3, 5, and 7. The odd ones. And then we'll do set C. 3, 4, and 7. Or back up. 3, 4, and 6. We'll do it that way. All right. Now, those are our 3 sets. And let's answer a few questions. This kind of pulls it all together. Everything that we talked about with sets kind of is used when we're talking about complement of a set. So let's answer this question first. What does that question even ask? All right, it's asking, is B a subset of A? Is B a subset of A? Are all the elements in B in A? 1, 3, 5, and 7. 1, 3, 5, and 7. So they are. So B is a subset of A. Now, what that allows us to do then is to talk about B complement. And the way it's just like an apostrophe is all that is. And you'll hear it called B prime. And it's just a little apostrophe there on the set B. And what that means is it's the complement. B prime is the complement of set B. Okay, so it's just like an apostrophe notation on the set name. So the set is named B. We put a little apostrophe on it. That's called B prime, and that's the complement of B. The complement of B would be, since B is a subset of A, it's all of the parts that are in A that are not in B. So that would be 2, 4, and 6. The elements that are in A that are not in B is B complement. B prime, B complement. Mean the same thing, okay? So A, what we're doing is we're treating A as like the universal set. That's what we're kind of doing in this problem, is that the larger set is the big picture. B is a subset of that. So when we look at the subset, if B is a subset, then we can do B complement and get everything that's not part of B. Okay. We can do the same thing with set C, because if we ask for C prime, that would be, what numbers would be in C prime? So we look in set C, it's got 3, 4, and 6. So in set A, basically we can, just kind of mark those out. What numbers are not marked out now in set A? 1, 2, 5, and 7. So maybe the marking out kind of can help you see that complement of that set out of that. So the complement are the parts of the larger set that are not in that smaller set. All right. In this particular section of the book, there's a little set operations box on page 6 that reviews all of these things. in your textbook, there's a green box. That's a great kind of one-page notation deal. The green box about set operations. Set operations. If you'll look at that box, or have that handy when you're working some of this stuff with sets, it is very useful to keep you kind of on track as far as some of the notation out of that, because that's a lot of the hard part of math is all the funky notation we use, because we think it makes it better. All right. Let's move on to the next section and go from there. So we're still going to be using the idea of sets in this section. So kind of lumping these together in one, and then we'll take a little short break here in a little bit after we finish this section. Some stuff. So real numbers and their properties. So section R2, real numbers and their properties. All right. When we talk about the real number system, there are a lot of different kinds of numbers inside of that. And it's kind of like you've got this huge box of numbers that exist. And then you've got all these smaller boxes inside of those. Okay. So that's the way I try to explain this with the real numbers is you've got a really big box to start with. Okay. So draw yourself a big box. This largest box is the complex numbers box. Okay. Complex numbers are numbers that have the I in them. Some like 2I, 6 plus 4I. And you remember I is the square root of -1, if you remember from an algebra class from sometime in the past. Not super important. The name of the section is the real numbers. The complex numbers is the biggest box of the numbers that we deal with. Inside of the complex number box is this slightly smaller box, but still a pretty big box. That's the real number box. So I'm going to draw another box, and I'm going to use a different color so that I can kind of do better. So inside of that, I'm putting this blue box, and this is going to be the real numbers. The real numbers are those numbers that we deal with regularly in a math class. We will deal with complex numbers later on, but the first kind of half of this class, you're not going to deal with complex numbers very much. But real numbers we will deal with. Inside of the real number box is another smaller box. Okay, so I'm gonna go green with this one. So you got this box here, and that's going to be what's called the rational numbers. Okay. And then there's another box that's kind of right there at the same level beside that, that's the irrational. Rational numbers are their own set, but they are part of the real number set. So they're inside of the real number box. They're also inside of the complex number box. Okay. The irrational numbers are inside of the real number box. They're not inside of the rational number box. You can't be rational and irrational at the same time. That's not possible. Okay. So rational numbers are in the box inside of the real number box. Okay. Rational numbers are numbers that can be written like fractions. The first 5 letters of that is the word ratio, and we deal with ratios. Normally we write that as a fraction when you put things in a ratio. So fractions are what rational numbers are. So that would be numbers like 3/4, -7/9, something like that. Are good examples of numbers that can be written as fractions. There's an infinite number of those. We couldn't list them all. Okay. Inside of the rational numbers box is yet another box. And I'm going to go with the dark blue here. Inside of this box is a box called the integers. Integers. E-N-T or I-N-T-E-G-E-R. Integers. Integers are the numbers that are not fractions, but could be written as fractions, like negative 165. I could write that as a fraction by writing negative 165 over 1. So that integer is a whole number that's positive or negative. That's what an integer is. Whole numbers that are positive or negative. You could have negative 6, negative 3. Those are all integers out of that. Inside of the integers box is another box that is the whole numbers. Whole numbers are the counting numbers. We already talked about the natural numbers, and we'll put that box in here now. Naturals. The natural numbers are the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And so on. The whole numbers adds the 0. You got 1, 2, 3, 4, ... It keeps going forever. The whole numbers adds a 0 to that. Okay? So natural numbers, that's the most inside box. That's the furthest one in. And it's the counting numbers. And then it's inside of the whole number box. And that whole number box has the natural numbers in it. The whole number box is inside of an integers box that puts the negative numbers in it. Okay? And then the integers box is inside of the rational numbers box. So if you're inside this box, you're also inside of all of these other boxes. Okay? So whatever level you land at, if you're an integer like negative 6, you're in this box. But you're also in the rational numbers box, in the real numbers box, and in the complex numbers box. Okay? So the idea of the boxes kind of can help you in classifying numbers, which is one of the things we're going to do in this section, is classify what kind of number is this. If it's a natural number, then it has to be all of them. But if it's a rational number, if it's like the fraction 3/4, then it can't be any of these because it's not in that box. It's in this box, and this box. Okay, so as we go through this, we're going to try to classify some numbers and use this box idea to help us do that. I think the box idea kind of helps you give some sort of concrete idea out of it. The irrational numbers box over there, I didn't write anything in it. That would be numbers like square root of 2, square root of 5, and 3. Any kind of square root that doesn't, that's a decimal that runs on forever and never repeats, and all that stuff. That's an irrational number out of that. Any square root of a prime would be considered an irrational number. Pi it's also considered irrational. I don't remember pi from maybe geometry class. It's not just 3.14. It's got a whole bunch of decimals after that, 59, 196, and something like that. It's a whole bunch out of that. And then, all right, so let's get into classifying a number. So let's take a set A, and I'm just going to put some numbers here, and we're going to classify those numbers by listing out what sets they belong to. Okay, so -8, -6. Let's do -12/4, -3/4, the number 0, 3/8, 1/2, 1, square root of 2, square root of 5, and then the number 6. Okay. All of those numbers are in set A. And what we're going to do is get the subsets that fit the different kinds of numbers, okay? So we're going to list the subsets. We'll start with one that we've already worked with a little bit, the natural numbers. Okay? Out of that set, which numbers are the natural numbers in that set? Remember, the natural numbers are the counting numbers. 1 and 6. That's it. 1 and 6. 0 is not a natural number because we don't start counting at 0. We start counting at 1 normally out of that. So natural numbers. Remember that I'm going to kind of review the notation for each set here. Natural numbers, the notation is that capital N with the double bar on the diagonal. That's how we normally notate natural numbers. So if you see that, you know, oh, they're talking about the natural numbers out of that. Okay. The next set that we want to look at or subset is the whole number set. 0 is a whole number, but remember our box idea. What else is a whole number? What else is in the whole number box? All the natural numbers are also in there too. So the whole numbers, it has 0, but it also has 1 and 6 in it too, because the natural numbers are part of the whole number set. Okay. The notation for the whole number set is a W, capital W, but then just put a double on the first kind of diagonal there for the whole numbers. That's how we notate the whole number set. Okay. Well, let's kind of keep climbing out of our boxes here, and the next box would be the integers box. Remember, integers are numbers that are positive and negative whole numbers. Okay, so we know that what numbers are integers in set A there? All of the whole numbers. So we got 0, 1, and 6. But what other ones? There's one more that's kind of in disguise there. Right there at negative 12 over 4. Does that reduce? Oh, yeah. The negative 3, right? So technically that is also an integer, even though it's in disguise. So you've got to look for that. That's one of the things that this is not a terribly difficult thing. So they try to squeeze in kind of tricks every now and then. And that's one of the tricks that they'll throw in there is they'll put a fraction in there that could actually reduce into a different kind of number. Okay. Now, this one is a weird notation for integers. It's not an I. It's a Z. And I'm not sure why. I couldn't tell you why they use Z. I'm sure it has something to do with some Greek mathematician from 1,000 years ago, and there's a Greek word that has the letter Z in it. It has something to do with integers. That's the notation we use because we've always done it that way. So Z's are integers. All right. Keep climbing out of the boxes. The next box would be the rational numbers box. Rationals. Remember, everything that's inside of the integers box can be written as a fraction because we can just put them over 1 and they'd be fractions again. So everything that was in the integers list is going to be in our rationals list, but then everything else that's a fraction is going to be there too. So we've got negative 8, negative 6, negative 12 over 4 is obviously a fraction. Then we got negative 3/4 is a fraction. 0 could be written as a fraction. 3/8 is obviously a fraction. 1/2. 1 could be written as a fraction. The square root of 2 and the square root of 5 cannot be written as fractions. They're decimals that never repeat and never terminate or don't end. So we can't use those in the rationals. And then the 6 and the 1 there. And that's, so the rationals is a pretty large set out of that. It includes a lot of different kinds of numbers. A rational number, the notation for that is a capital Q. And they put this little line kind of diagonally through it like that, just to notate that it's a special Q. The reason, I do know the reason for Q on this one, because rationals are quotients, and quotient starts with Q. Quotients is the word that we use for an answer to a division problem, and rationals are fractions, which are division problems. That's the reason for the Q. Now, the other set that existed that we didn't do much with here was the irrational set. And irrationals, what are the only numbers we didn't use out of that set A? Yeah, square root of 2 and square root of 5. Those are irrational. And the notation for irrational is just do the Q and then put a slash through it like that. That's irrational. It means it's not rational. If you're irrational, you're not rational. That's the idea of that. So you don't do a whole lot with irrationals as far as classifying sets out of that. But if you'll think about the box idea and kind of have that handy, that'll help you in classifying numbers in this particular section. And then, that's kind of the idea of the real number system is all of these different kinds of numbers are inside that real number box. Okay, we'll add the complex numbers later on in the course, maybe next week. No, not next week, but the next week 3. We'll get into some complex number stuff. All right, so now let's talk about properties that work with these numbers. Those properties are like the operations. Okay, so we're going to talk about order of operations. Order of operations, this is very basic math stuff that's been around and we've been using since we first started learning arithmetic in kindergarten, first grade. We started adding and subtracting and then maybe doing some multiplying later on out of that. So order of operations is, please excuse my dear Aunt Sally, as the way that I learned that. You may have just remembered PEMDAS. And but the P stands for parentheses. The E is for exponents. The M is for multiplication. The D is for division. A is for addition. And then subtraction. The thing to keep in mind is parentheses just really means a grouping symbol. So if it's a square bracket, that's the same thing as a parenthesis. If it's an absolute value symbol, the straight up and down bars with the number inside, that's a grouping symbol. So parentheses are grouping symbols. Exponents, those happen next. And then multiplication and division, those are the same level. You don't have to do multiplication first or division second. It's in order that you come across them in the problem. So it's left to right, multiplication, division. Those are the same rank. Addition and subtraction is the same way. Those are the same rank, left to right. Okay, so left to right. In that, so after you've done all the parentheses work or taken care of any exponents that are in the problem, then you're looking for multiplication and division left to right. And then you go back and do addition, subtraction, left to right. So when you're working with these, keep that in mind that multiplication, division, addition, subtraction are the same rank. They don't have to be done multiplication first and then go back and do division. You shouldn't do it that way. That's it. That's where folks get those problems wrong out of that. So there's nothing more frustrating than seeing those memes on Facebook that say only geniuses can get this right, and it's an order of operations problem, and then you're you're a math teacher and your wife's a math teacher and your family misses the problem and posts their answer and you feel bad because you feel like you've let them down. It's worse when your students put the wrong answer on there. So, but hopefully we can clear up any issues with that. The good thing is with the calculator, and we're going to kind of incorporate it some in this stuff because we're actually doing some math now. I'm going to show you how to get the calculator to do things. If you can type it in the way it looks, then it'll work it with the correct order of operations. So that's always a lifesaver since we get to use a calculator here. If you were in my high school class, I wouldn't let you use a calculator for the first couple of months, but I don't do that with college kids. You guys are, we're working toward a bigger goal here. So the first thing we want to look at are dealing with exponents, and I want to show you how to work with exponents and how to use the calculator to do that. So exponents, I think we all know how to do parentheses and multiplication and addition, division, addition, subtraction. Exponents are sometimes one of the things that gives us some problems. Exponents, you have this thing called a base, and then you have the exponent up top. The base is what gets multiplied the multiple times, whatever n is. So, for example, we'll be on example B here. 4 to the third power means take that base of a 4 and list it out 3 times. 4 times 4 times 4. I know that that's 64. If I want to do that with my calculator with the TI-84, the way to do that, or the easiest way to do that, is you type your base, so it's a 4, and then you're going to use the caret symbol, which is right here underneath the clear button. And you'll see whatever button I hit last highlights in red on the calculator screen there. So when I hit 4, it turned it red, and then the next button I hit was the caret symbol. So it highlights that in red. And then it gives me an exponent box up there to put whatever number I want in there. So I'm going to put the 3, and then I just hit enter, and it works it out. It says 4 times 4 times 4 is 64 out of that. So using the graphing calculator, type your base, caret symbol, and then whatever exponent that you need to work that out with. So that's handy on the calculator. You can write it out and work it out, if you want to. I don't figure that's something that a lot of us will do. Another problem that seems to come up when we're dealing with the exponents is when we take a negative number to an exponent. A lot of times we want to say, okay, well, that's negative 6 squared, and that's negative 36. That's not correct because it's negative 6 times negative 6. And when you multiply 2 negatives together, what do you get? A positive always out of that. So we know it's going to be positive 36. In the calculator, here's where the issue comes in with this, is we get such dependent on that calculator, and we'll just go negative 6 squared. So I'm just doing the same button sequence as I did with the 4 using the caret symbol. And it gives me negative 36. The reason it does that is because your calculator does order of operations like to a T. So the way it reads that problem is it says square 6 and then make it negative because the exponent happens first. That's not the problem that it asks us to work. It asks us to square negative 6. So to do that correctly in the calculator, you've got to use the parentheses. And the parentheses are right here above the 8 and the 9. So a parenthesis, negative 6, close the parentheses, caret symbol, 2. And there we get a negative 6 times negative 6 is positive 36. Be very careful of that. There's so many problems that we're going to use squaring or taking an exponent onto a negative number. If you're getting the wrong sign for an answer, it's going to mess everything up. So be very careful of that. Make sure that anytime that you're raising a negative number to an exponent that you use those parentheses. If you don't, it's going to give you the wrong answer. So again, if you can type it in like it's written, you'll get the right answer. Because sometimes they will actually ask you to do that, -4 to the 4th power, without the parentheses in there. And we know that that's taking 4 to the 4th power and then making it negative because of order of operations. But I'm typing it in exactly like it's written, -4 raised to the 4th. And it's going to give me -256, which is the correct answer for this one. But if it asked me to do -4 raised to the 4th with the parentheses, I'm going to put it in parentheses, -4 raised to the 4th. I'm going to get positive 256. Out of that. All right. Let's kind of start mixing it all together and doing more than one operation at a time. So let's evaluate example F. 4 times 3 parentheses squared plus 6 times 4. So if we did this with order of operations, it tells us to do parentheses, exponents, then multiplication and division, and then addition and subtraction last. All right, so if I did this just, one step at a time, I would do 4 times 3 first because it's inside parentheses. So that'd be 12, and that's going to be squared. And then I'm not doing the 6 times 4 yet because I hadn't got to that. And then I'm doing exponents. So I'm going to square the 12. 12 squared would be 144. Knowing multiplication tables there. And then the next step is to do multiplication division left to right. So there's no multiplication division here. There is here. So that's 144 plus 6 times 4, which is 24. So a long way about doing this. Obviously, we could do it much faster. And then the final answer is add those two together. 144 plus 24 be 168. That's step by step doing that. I'm not requiring you to step by step do that. I would like for you to know how to do it step by step. Just because that tells me you know order of operations. That's going to help you when we don't have numbers in there and we got letters in there. Okay. As long as you're getting the right answer here, if you can type it in like it's written on the calculator, 4 times 3 in parentheses squared, and I'm going to use the caret symbol. And then to get out of the exponent, you got to press the right arrow key up here in the circle to get down out of the exponent, and then it's plus 6 times 4. And I've typed that problem in exactly like it was written, and I hit enter. I get 168. That's same answer. Again, if I can type it in just like it's written, I get the right answer on these order of operations problems. Let's do this one. 6 divided by 3 plus 2 to the 3rd times 5. If I do that step by step, there are no parentheses in this problem, but there is an exponent. There's a 2 to the 3rd power, which I know to be 2 times 2 times 2, which is 8. And then, which one of those happens first? The 6 divided by 3 or the 8 times 5?
6 divided by 3.
Yeah. Multiplication and division are the same rank, but it should go left to right. So 6 divided by 3 is going to happen first because it's the closest to the left. So that's going to be 2. And then technically, the next thing that happened would be the 8 times 5, which would be 40. And then we would add last, which was 42. Again, if you can type it in like it's written, you can get the right answer out of that. But knowing that order of operations is always better about that. So I'm going to type it in that way so you know what the calculator is going to look like. So to type it in, I'm going to do 6 divided by 3. So 6, and then I hit the division symbol, and it's going to give me that slash mark, which is the, division symbol. It's going to look like, it's doing a fraction, but it's doing the division. 6 divided by 3 plus 2, caret symbol to the 3rd. Press the right arrow key to get out of that. times 5 and hit enter, and there we get 42 as a result out of that. So we, again, if we could type it in like it's written, we can do that. All right. Let's get to one that's a little bit more complicated looking, but it's not any harder. It just looks tougher. 4 plus 3 squared over 6 minus 5 times 3. So it looks like a big old fraction. And the way order of operations works for this is you want to work top part, bottom part separate, and then work it as a fraction, as a division problem. So if I did the top part, the 4 plus 3 squared, that's going to be 4 plus 9, right? And then the bottom part, the first thing that should happen in the bottom would be the 5 times 3. So that'd be 6 minus 15. And then do the addition. 4 plus 9 is 13. 6 minus 15 is negative 9. And then does negative 9 go into 13 evenly? No. So I'm just going to leave it as a fraction like that. With the graphing calculator, you can actually type it just like it's written out of that. And the way that you can do that is hit the alpha button, which is the big green button up here in the top left, and then the first button on that row, and it gives you this menu for that. So it's the alpha button and then the y equals button, and that opens up the fraction menus. It allows you to type in a fraction. So I'm gonna hit enter for number 1 because that's the fraction n over d, and it gives you this. It looks like a fraction now, and you can type in exactly like the problem is written. 4 plus 3 squared. And I'm just pressing the right arrow key to get down to the bottom. And on the bottom, it's 6 minus 5 times 3. So I've made the calculator make it to where I can type it in just like it looks. And then just hit enter. Absolutely. Absolutely. All right, so to get the fraction on the calculator, you're going to hit the green alpha button and then the y equals button, and it should pop up this menu. This is only on the TI-84. The 83 does not do this. Okay, so alpha y equals pops up this menu. I'm going to select number 1 because that's the fraction. And then 4 plus 3 squared. Then I press the right arrow key until it gets to blinking in the box in the bottom. Okay. And then I'm hitting 6 minus 5 times 3. And then if for some reason your calculator didn't give you a fraction as an answer there, and it gave you the decimal for that, so let's say I'll make it give me the decimal. It gave me that as an answer. The way to change it from a decimal to a fraction is to hit math and then hit enter twice, and it'll change any decimal that can be changed to a fraction. It'll change it to a fraction. Okay. Math, enter is how you change a decimal to a fraction on the graphing calculator. Okay. All right. Let's do one more of those. Let's say we had negative parentheses negative 3 to the third plus negative 5 over 2 parentheses negative 8 minus 5 parentheses 3. And if we do order of operations and we work the top part and the bottom part separately, if we're going to do it by hand, negative 3 to the third power just means negative 3 times negative 3 times negative 3, which would be negative 27. But then it's got a negative in the front. So negative 27 times negative would be a positive 27 plus negative 5. And then on the bottom, 2 times negative 8, we can do that. It's negative 16 minus 5 times 3 is 15. And then we just do that addition and subtraction there. 27 plus -5, so that's like subtracting 5, so that's going to be 22. -16 minus 15 is going to make more negative, so that'd be -31, and that's not going to reduce, so we leave that as that fraction. On the calculator, if we go to type that in, again, we're going to hit alpha y equals and get that fraction. And then I'm just going to type it in exactly like it was written, which was, just like that. Okay. Negative, parentheses, -3. Close the parentheses, raise to the third power. Right arrow key to get out of the exponent. Plus, parentheses, -5. Right arrow key to move to the bottom. 2, parentheses, -8. Close those parentheses, minus 5, parentheses, 3. Again, it should give me a fraction as an answer here because I've already picked fraction. And I get the -22 over 31. The difference, I've got the negative on the 31 here. It technically does not matter where that negative is at. The calculator puts it out in the front of all of it. If you put the negative with 22 or with the 31 or out in the front of it, it's all the same. It's just a negative fraction. It doesn't matter which one you put the negative in. Did you use the negative sign or the minus sign when you were putting those negative numbers in it? If you're going to use a negative sign, you got to use this one down here beside the enter button for the negative numbers. That's the most common error that could happen there.
Okay, maybe that's what I did.
Yeah. They look very close to the same when you're typing them in on the screen, but it is the calculator reads them differently. If you use a minus sign, it will give you an error there to see if that's what it was. And see if that'll clear it up for you. All right. All right, let's do some evaluating with variables in the problem. So let's try to do that. I'll show you how you can use your calculator to help you do that. Evaluate, again, just means find the answers. But we're going to have when x equals -2, y equals 5, and z equals -3. Okay. So they're telling us what the variables are equal to, and they're going to give us an expression to evaluate. So like maybe -4x squared minus 7y plus 4z is the expression that they give us to work out here. So what we're supposed to do is just replace the variables with the number that they said they were. So I would rewrite the problem, -4, and then everywhere that I'm replacing a variable, I'm going to use parentheses when I put that number in there. So I'm going to put parentheses, -2 squared, like that. And then -7, parentheses, 5, plus 4, parentheses, -3. If you will have that habit of using those parentheses when you replace the variables, it will save you some headache on a few problems as you go along there. Because if you don't put those parentheses and you type it straight into the calculator like it's written, it's not going to work out the right way for you. So be in the habit of doing that with the calc. And so once you replace those, you can follow order of operations and work it by hand if you want to, or you can just plug that into the calculator just like it's written here on the second line and work that out. So I know that -2 squared is 4, so this is -16. This is -35. This is -12. 40, 51 minus 12, -63. That's what I should get if I go to the calculator and just type that in. -4 parentheses -2 squared minus 7 parentheses 5 plus 4 parentheses negative 3. And again, make sure when you're doing a negative number, you use the negative sign that's down by the decimal and enter there. And hit enter. It's negative 63, which is what I got. So that's the easiest way, I think, to use your calculator to do that type of problem. Let's do another one of those, and then we'll do the easy thing last here for this section. Let's say we had 2 parentheses x minus 5 squared plus 4y over z plus 4. Again, I would plug in the stuff for x, y, and z. I know x is still negative 2, y is 5, and z is negative 3. So I'm going to say 2 parentheses, and then I'm going to say negative 2 minus 5 squared. And I'm putting in an extra set of parentheses there just to be safe, plus 4 parentheses 5. And then z is negative 3 plus 4. And feel free to do some of this, some of the parts of it, that don't look as bad, I might do by hand. And so when I'm typing it in the calculator, instead of writing 4 times 5, I'm just going to write 20. And instead of negative 3 plus 4, I'm going to put a 1 because I know that that's what that is. So maybe that can save you a few keystrokes there. So again, this is one of those big fraction deals. So I'm going to hit alpha, y equals, get that fraction out of it, 2 parentheses, and then a parentheses with a negative 2, close those parentheses, minus 5, close those parentheses, squared, plus 4 times 5, which I know is 20. And then on the bottom, maybe I'm not as confident about my adding and subtracting of negative and positive numbers, so I'm just going to type that one in. And there I get 118 as my final answer for that one, which is correct because this is going to be 7 squared is 49 times 2 is 98 plus 20 is 118 over 1. So that one didn't. Technically it is a fraction, but you don't have to write it if it's over 1. You don't have to write the fraction form out of that. All right. All right. Next thing is simplifying an expression. Same section. Just a few examples of simplifying an expression using order of operations and like terms out of that, and then we'll take a short break and then come back and try to do some other sections here. Simplifying an expression. The key is like terms. Like terms means it has the same variable and same exponent on that variable to be a like term. So x's add to be with x's, x squareds don't add to plain x's, but x squareds can add to x squareds out of that. So first example, 6 plus 9 plus x. And so that's like terms for this one. 6 and 9 are both plain numbers, so they're going to go together. So 9 plus 6 would be 17, or excuse me, 15. 15 plus x. And you combine the like terms. That x doesn't have anybody else that's like him, so it just goes on the end there. So if it doesn't have a like term, it just kind of copies down. 7 minus 2 plus 3x plus 6 squared plus 5x. So here we got to do a little order of operations because you got some parentheses and some exponents going on there. So we're going to start with parentheses. If I look inside of these parentheses, I can do the 7 minus 2 because that's a lot. Those are like terms. 7 minus 2 is 5 plus 3x. And then I can do the exponent there. 6 squared would be 6 times 6, which I know is 36. And then the 5x is there. Now I look for like terms. 5 and 36 are alike. 3x and 5x are alike. So I'm going to put the like ones together. 3x plus 5x would be 8x. They're both positive, so it's positive 8x. And then 5 plus 36 would be 41. And then that's the final answer there is 8x plus 41. So it's following order of operations still. You'll never get away from order of operations. It always is in the game. And then technically it doesn't matter if you wrote 41 plus 8x, that's the same answer. I wrote 8x in front there just to show it doesn't matter what order, because example L, I wrote the x last. Later on, when we do polynomials, we'll start putting them in order a little bit more, but we'll have more stuff going on there. So that's kind of what's happening there. Let's do a one with some multiplication involved, maybe something like 5 parentheses 8y plus 3 parentheses 2y minus 6 parentheses 7. A lot of multiplication in that problem. So order of operations tells us, okay, do parentheses, exponents, multiplication, division left to right, and then addition and subtraction last. So we're going to do that multiplication. 5 times 8y, 40y, 3 times 2y, 6y, and then 6 times 7, 42. And then we're going to do the addition and subtraction. But we're looking for like terms. Remember, like terms have to have the same variable, same exponent on those variables to be like terms. 40y and 6y are the same kind of thing. They both got y's. So we're going to add them together because it's addition between them. So that'd be 46y minus 42. The 42 doesn't have anybody else like it, so it's just kind of copied down. And then that's the final answer is 46y minus 42 out of that. Very simple idea out of this. Nothing crazy coming up in section R2 there with that stuff. Okay. All right. Let's take us a